Coulomb's law shows the magnitude of the force, the electrostatic force between two charged particles. And here it is. Q1 in this equation is the electric charge on particle 1, Q2 the electric charge on particle 2, and d is the distance between them. The Coulomb's constant in this equation is about 9 times 10 to the 9 Newton meters squared per Coulomb squared. Notice that if the sign of the two charges is the same, the force will be positive, so they'll repel each other. And if the signs are opposite, they'll be negative, so they'll attract each other. So protons attract electrons, but they repel other protons, and electrons repel other electrons. This is a very strong force. You can see that by the size of the constant, Coulomb's constant. And we can illustrate the strength of this force by doing a little thought experiment, which can't ever really be done. And that is, if we have 1 kilogram of matter here, 1 kilogram here, separated by 1 meter. Now let's imagine if we could magically switch off the electric charge on all the electrons in each of those kilograms, so we just have the electric charge of the protons left. What would be the repulsive force between these 2 kilograms? And this will illustrate just how strong this force is. So first of all, let's calculate the amount of charge on each of these kilograms. So in a normal kilogram of matter, about half a kilogram is the mass of protons, because electrons are negligible in mass compared to neutrons and protons. And at least in the light nuclei, like what we're made of, the protons and neutrons are roughly equal in number in each nucleus. So in each kilogram we've got about half a kilogram of protons. And each proton, the mass of a proton, is 1.7 times 10 to the minus 27 kilograms. We can figure out the number of protons this way, because the number of protons times the mass of one proton is equal to the total mass, which in our case is half kilogram. So and if you do this, you get about 3 times 10 to the 26 protons. Okay, so that's the number of protons in half a kilogram of normal matter. Now the charge on a single proton is 1.6 times 10 to the minus 19 coulombs. And if you multiply this many protons by the charge on one proton, the total charge in our half kilogram is 4.8 times 10 to the 7 coulombs, 48 million coulombs. So that's the charge on the protons in each kilogram of matter. So there's about minus 48 million coulombs on the electrons, which causes normal matter to be neutral in charge. Okay, so now we know the magnitude of the charges on our 2 kilograms. So let's put this in here. Million coulombs, 48 million coulombs, separated by 1 meter, that gets squared. And when you calculate this, you get 2.1 times 10 to the 25 newtons. So a really large amount of force. This is between the protons in 2 kilograms. Now, how do you get your mind around that force? Well, you can't, but we can express it in sort of familiar terms. For people that live in the Atlanta area, you're familiar with Stone Mountain. It's a great big old rock sticking out of the ground. Its weight, the weight of Stone Mountain, is about 630 million tons. Which is about 5.6 times 10 to the 12 newtons. So there's a large unit of force that we can use, at least in the Atlanta area, to talk about real large quantities of force. in different units. To find what this force is between our 2 kilograms in stone mountains, just divide this by this, and when you do that, you get, it's about 4 times 10 to the 12, 4 trillion stone mountains. So amazingly, if you could magically switch off the charge on the electrons in each of our kilograms, being a meter apart, they would repel each other with a force that's about 4 trillion times the weight of Stone Mountain. So it's a really strong force. Normally you don't experience these forces because electrons and protons are so evenly mixed in normal matter. A kilogram of matter has almost exactly the same number of electrons as protons, that we don't even normally feel electrostatic forces between 2 objects. On a microscopic scale, it's very important because it holds atoms together and holds molecules together, and that very strong force is what gives rise to solid objects as we know them and most of the dynamics of nature around us that we experience.